All right, so, okay, so hopefully the exam wasn't too bad. As was mentioned, I know a lot of people did not notice that did not notice the existence of question 7. Like, because you had, I'm not going to go too much in detail into it because I think I still have some people who need to make it up, but there was a question you had to that where I had the instructions on the left, and then I had a question on the right, but there was a scroll on so that there was another question and people didn't realize you had to scroll. So some people missed that on their individual exams. So I'll try to figure out the most reasonable way to deal with that. There's a couple different ways I can deal with that, which is the most reasonable ways are using your group answers as your answer and giving either like half credit or full credit based on your group answers on the individual exam. Or I could just simply nix that question from the individual exam and only count it in the group exam. There's different ways I can do it. I will have to take a look at your exams and see what is the most fair, because I feel like that's not completely your fault. You know, if you didn't see a question, you know. So but again, and this would be a real issue if we hadn't done it as a 2-stage, because with the 2-stage, at least I have an answer of some kind. All right, so before we move on, how was the 2-stage exam? Did people think that was useful? Yes.
A lot of theory, but then when you like get to the group part and it's the same exact exam and you like know everything you got wrong from the first part, that's kind of a downer. So like maybe similar exam, like very similar, but not.
That is the biggest criticism that has actually been reported about group exams, which is that it is kind of a downer to know what you got wrong immediately. That being said, I am very good about doing partial credit. Like, the only way you don't get partial credit is if you don't write something, or you write something that's very, very wrong. Like, for instance, in the 1051 class where I asked, name a famous computer scientist and briefly explain why they are important. I have got an answer. I got some memorable answers there, like Alan Lovelace, which was an malapropism there, and there was
say Newton, right?
What?
Did someone say Newton?
No, somebody did say, mix up Steve Gates and Bill Jobs. Steve Gates and Bill Jobs. Yeah, exactly. No, they said, like, I think they said Steve Jobs was the inventor of Windows.
Oh.
So like something like then, and one person made a depressingly number of people thought Ada, the Countess of Lovelace, was was American, not British. And then some people also confused her with Grace Hopper somehow. And again, that was on the practice exam, so not really sure how that happened, but hey, but like, you know, really bad answers.
I think the exam kind of hard because sometimes if you're under time pressure,
yes,
nothing really comes up. And then after you're done and you just do section, you're like, oh, I know that, but like it's too late.
That's a good point. So we also got a mention in chat saying, I feel like there wasn't enough time in the group exam for actual discussion. My group kind of just said, who thinks they understood the question X the best, and copy pasted the answer. Again, this is like all experimental. I'm trying to do this and trying to improve this. And for the intro exams, I think doing the same exam twice is good. I think for the second exam, I will probably do what you suggest, which is similar, but different questions. Or maybe I can write some questions that use the questions from the individual exam. Like you saw that, for instance, where question 6 had to be used for question 7. Or sorry, it didn't have to, but it made your life a lot easier. Maybe having one big semi-challenging problem. Yeah, I think my biggest thing is discovering that different levels of classes have different needs from the group exam, you know. So again, it is yeah, it's an experiment. I'm not like a research experiment, but like an experiment trying to figure out what is most beneficial to my students. Because I do try to do that. Sorry that you're beta testing for future semesters. But I do like the fact that if you completely miss something, there's the opportunity to learn. That's what I really appreciate about this format. But yes, and another thing, I think maybe having one big semi-challenging problem so we can all work on it and all contribute. It's true, but I always am a bit wary of all or nothings, but at the same time, we do have the clause that you can't do any worse. So there is that. So those are all things to consider. So, okay. Now let's go ahead and open up Canvas and see what's coming up. Now, as I mentioned, Yom Kippur starts tonight. So first off, any of those who are going to be celebrating, I guess, best word I can come up with. I hope you have an easy fast. That's my two-factor authentication, actually, not my not a spam call for once. So there we go. But as a result of it being Yom Kippur, I will be out. I will be completely uncontactable for sundown tonight to sundown tomorrow. Okay, so don't expect an email or a reply back from me. Okay. I did get a number of emails saying, hey, and Discord messages saying, hey, can you push back the assignment due date, which I did for the maze problem. I will be happy to answer any questions about that. And I'm just going to check out the due dates that we have here. So we have, yep, I have it due today. Again, I try to be flexible about these due dates. And then I have recursion on the 13th. I will definitely hammer a lot of stuff on recursion on Thursday. So a couple things, but I want to mention a couple things that you should know before you get started with it, because this is week 7's homework, which is recursion. Okay. Go, come on. There we go. Okay. So with the recursion one, almost all of your problems are going to be using this algorithm where I define board and position very loosely. Your position might be a specific column, like choosing which, keeping track of which column you're at. Your position also might be row and column, right? It might be, 2 coordinates, or it might be a single variable that like a single number that you split up into a row, that you calculate a row and column for. Position is abstract, as is board. But this is the generalized algorithm for a problem-solving process called recursive backtracking. And the idea here is that there's this method of searching for answers called brute force. I have a friend who likes to say brute force always works, because that is, and when he tries to go and solve something, he'll first brainstorm a brute force solution. The issue with brute force is essentially it's like BOGO sort. You basically go through all possible the entire solution space at random until you hammer out a correct answer. It's not very methodical, but you can be more methodical. And yes, I will be explaining how to check for walls and stuff in the maze. Okay, so with the recursion, oh, I didn't realize I wasn't sharing my screen. Okay, I will do that now. Okay, so with the recursion problem, we have, some board, and what we say is that basically, if your position is such that there's nothing left to solve, in other words, you've solved everything, all your squares have been solved or whatever, or you've put a queen down in every column, or you visited every square, or whatever it is. So if you're at a position where you are done, return true. So notice that we have return trues and return false. A return, so this is recursive. Notice that we have a solve and a solve here, and I'll go through this, but this is an important thing that I want to just mention first. The return trues and falses are signals to the solve method that calls you. If you are a solve method, you know, in the middle of this recursive function, and you call another solve method, you know, you recursively call solve. If you get true back, that means we found an answer. Great. I'm going to return true. Okay. I'm going to keep returning true, basically, and I'm going to report back to the person who told me that we found an answer, and they're going to report back to the person who called them that they found an answer. That's what once you hit a return true, it basically starts a cascade of all these return truths. Make sense? If you hit a return false, that means that you have hit a wall. You are now at a position where you need to backtrack and re-examine your choices, the choices you made that led you to there. In other words, if I call solve method on something else and I get a false back, that means that trying to solve from this point on is not going to work. So I'm going to excise that entire branch. And what this allows us to do is that we have this entire tree of solutions. And as soon as we find that the branch of the tree that we're trying to solve is not valid, we don't have to check all the twigs off of it, you know. We can just cut off that entire branch and not have to search it. Basically, we are being much more efficient about how we're going through our search space. So the way this works is that we say, if there's nothing left to solve, great. Then if basically this is if you call somebody and that somebody says, hey, I've hit the end, there's nothing left to solve, so we're at the end of the puzzle, so return true. Otherwise, if you're in some position, you basically have some choices. For Sudoku, that's whatever number what number you should put in the square. For a queen, for the 8 queens problem, that's what row should you put your queen in. So for each of the possible choices, you basically want to ask, is this a valid choice? Can I put this queen in this position? Can I put this number in this square? If I can, mark down that I made that choice. In other words, like put the queen there in your array or put down that number, and then solve the next position. So this is our recursive call, and it's inside an if statement. If solve is equal to true. So I'm going to call the solve method with the position after me, and I'm going to say, hey, if that answer came back as true, that means that somewhere along the lines down the line we hit this statement, that we got to the end. So that means I can return true, which will return true to the person who called me, which will return true to the person who called them. However, if I get back a false, I'm not going to return true. Instead, well, I marked that position with the choice, but it's not going to work. So I'm going to unmark it. I'm going to remove it, or I'm going to remove the queen, or I'm going to remove what I put down from this spot and move forward. And then I added this because if you not remove it for some reason, then you want to make sure you definitely remove it here if you go through the entire for loop, because we need to return false to our parent to say, hey, I tried every possible combination, but the current way the board is set up, there's no possible solution. So now the important thing here is that there are 3 problems on this. You get to choose one of 2 chess problems, and then you have to do Sudoku. So you don't have to do both the 8 queens problem and the knight's tour. You get to select which one. The 8 queens problem, basically you want to position 8 queens on a board such that none can capture each other. If you know nothing about chess, then it's very simple. Queens are the most powerful piece. A queen can basically move any number of squares in a single column, any number of squares in a row, and any number of squares diagonally. Okay, so they can move like rooks and bishops, which are 2 other powerful pieces. So they can hit anything on a row, a square, or diagonal. Right. So annotate like this. So this queen, right over here, threatens this entire space around her. Now the 8 queens problem says, hey, how do you put 8 queens on a chessboard so that none can capture each other, none threaten each other? Meaning that none are in the same row, same column, or same diagonal as each other. There are like 91 solutions to this problem. But all I want is one, right? As soon as you find one, you're good. This is a solution to this, right? Notice that no queen is on the same solution to each other. Also, what's very interesting is that this entire chessboard was generated by basically a few lines of code, because I did this in LaTeX, and apparently there was a chess package for LaTeX because people are like that. The Knight's Tour is a bit more challenging. It's basically saying, hey, let's choose a square for our knight to start on. And then we want the knight to visit we want basically to move the knight and visit every square exactly once. Okay. So, and the knight has a very interesting way of moving. It's 2 in one dimension and 1 square in the other dimension. So either 2 in a row, and then 1 in a column, or 2 in a column and 1 in a row. So these are, and it ends up being like an L shape. Okay. So I highly recommend that if you do this one, you'll want to start off on like a 5x5 board rather than like a 4x4. Sorry, rather than an 8x8, because this search space can be quite big. And unlike the other problems, you have to worry about going out of bounds. Okay. Now, the Sudoku puzzle, I will definitely go into detail about how that algorithm works on Thursday. But Sudoku is a very, very good, fun type of puzzle where basically you want to establish, where we want to put numbers down so that in a 9x9 grid, so that no number is repeated in a row, no number is repeated in a column, and no number is repeated in a 3x3 square. Which again, I will go into more detail on that on Thursday, but you can look it up. These puzzles are nice, brain exercises. They get you thinking. There's a lot of logic involved. There's logic involved here, but not the kinds humans will use. This is more of the brute force, the computer can check it kind of logic. It is. So there's this dungeon in Dungeons and Dragons. It's the Tomb of Horrors. It's full of nasty traps. And basically there's all sorts of traps that deal with all the magical shenanigans wizards can deal with. It's very lethal for characters to go in. And basically it's just meant for DMs to troll the players. It involves a lot of thinking for the players to get through and a lot of trial and error. The easiest way to get through that, though, is the most mundane. You hire a team of miners and they just simply hit the walls of the dungeon until they get to the treasure room. It's boring, completely defeats the point of the puzzle, and that's kind of exactly what we're doing here. There's no logic or elegance involved in how we solve Sudoku. We are bringing basically a hammer to this puzzle and just simply going through and solving it with utter brute force. There's a lot of logic involved in telling our computer how to do the brute force, but if you're expecting something elegant, look somewhere else. It's a different kind of elegance. It is the elegance of simplicity. The extra credit here is that Project Euler has problem 96. These are examples of Sudoku puzzles. The extra credit is solving problem 96, where basically you will have where there's a text file of Sudoku puzzles. Okay, here's the text file. You read this in automatically. So you read a line and then you discard the first line, and then you read 9 lines and store that in an array. You solve it and just do that for 50 puzzles. Project Euler is designed so that any computer should be able to solve a puzzle, that if you've got a program and you run it, should be able to solve it in less than a minute. Yes.
Are there like any edge cases where it's like the Sudoku is not solvable, and then you can output that as solvable?
I mean, I suppose there are Sudoku where, I mean, if you're given like something where it's in a legal starting state, then yes, it's unsolvable. But otherwise, every Sudoku puzzle is solvable. The trick is when you're designing a Sudoku puzzle to make sure it only has one possible solution. It is and designing puzzles is a very challenging thing. One of my favorite examples is designing a crossword puzzle, which there was one that predicted I think the outcome of the Bush v. Gore 2000 election. And the idea is that basically that the answers that you spelled out would basically say Bush won or Gore won, depending on what answers you put in the questions in the certain in one grid. It could basically, each thing had multiple answers, which was very interesting. Making puzzles that have one solution and then all is challenging, but then there's some things where basically if you're trying to play a joke like that, like where basic, or basically show that, give it a bit of a flair, I guess, a flourish. That can be really challenging. Anyway, enough about that. I will go into that on Thursday. A lot of you want to know about the I feel are stuck on the maze solving, so I'm going to go into that. So we have these 3 files. Hopefully you have messed with them at some point, right? Maze grid panel, maze, and cell. All right, and I think the problem that you're having is, it was expressed by the question I got in chat, which is, can you explain how to check for walls move in a direction for the maze program? That is basically the sum of all we need to do for the maze program, but it is actually it is not necessarily trivial. And if you've been beating your head against the wall for a few hours against it, it can be hard to see what the answer is. So maze and stuff. Great. Okay. Yes, my naming scheme is excellent. All right. Don't need that. We're going to just simply drag these over here into the SRC folder. Okay, boom. Okay. So what we need to do for the maze grid panel. So the question was, so first off, how do you move? How you move is actually not so hard. You move into a square by pushing it to the top of the stack. And then what we're going to do is we're going to have a while loop over here. And basically the while loop says until we are done with the puzzle, right? As long as we haven't found the finish spot. Oh yeah, yes, I am. I was just testing you. So there's a couple different things you want to try here as your while loop. Actually, the while loop, the big loop that controls when you're done with the puzzle, should be the last part that you fully finish. You'll want to actually put in so like, for instance, I'll put in a while true over here, a while true loop, meaning that this will run forever, right? And then I can like break out of it manually. We'll figure out what the solution is later. Instead of putting in the while loop, I'm going to actually put in a for loop. For int I in, sorry, I've been working in Python. It's actually challenging to have to switch between 2 languages every day. For int I is equal to 0, I is less than, let's say 10, I plus plus. Okay. And what we're going to do is, rather than running through this loop like forever or not having an end condition, we're just going to like move 10 squares. Okay. The way that I can move, okay, is first off, what I'm going to do is I'm going to say, hey, this current square I'm in, cell current, assuming I can spell, is equal to stack dot peek. That really should be the first thing you do, peeking to see where you are. Okay. And then how do you move to another square? Well, the way you move to another square is, since the top of the stack is where we currently are, to move to another square, you say current dot, sorry, you say stack dot push, and then you say what square you want to move to. Generally, that will be something like maze, which is our internal grid, and then give it the row and column that you want to move to. Obviously, you can't teleport because we're hoping to draw an entire thing here. Okay, more on that so just keep that in mind. The other thing but the more important question is, how do you check for walls? It's actually not so hard. So let's go ahead and assume we want to check if there's a north wall. That's the first thing we want to check. All right, so the pseudocode says basically if there isn't a north wall, and I haven't been there yet, right? So if there is not a north wall, so if our current cell dot north wall, if that is not true, if there's not a north wall, right? And I haven't been there before, okay? So the way we check if we've been there before is that we're going to use visited, okay? Visited is a function I wrote in here, which takes in a row and column, gets the row and column for that cell, and gets the color of the cell. Because the idea here is that you're painting your cells as you're moving forward, okay? So if the color is white or red, then you haven't been there yet. White being an unvisited cell and red being a finished cell, the finished cell, the end point, right? If it's white or red, you haven't been there yet. So return false because it's not been visited. Otherwise, you've been there, so return true. So what we're going to say is if we haven't been to the north wall and we've not visited, if we don't have a north wall and we haven't visited the square above me, which is current, well, we need two dimensions. We need the row and the column. So, and this is where one of the biggest annoyances can come up, okay? Which is we want to go, which is that basically that X and Y and row and column are completely messed up, right? X and Y, right? X, you go this way, but the row, specifying what row you're at, which is the first dimension in row column notation, specifies the top down, right? So that's kind of reversed from what you normally think of. Furthermore, in computer science, which may have not been explained to you, well, simply put, your screen is like, the way graphics work is that your screen is a bunch of squares on a coordinate plane. The issue is, and let me just draw it out here, where is the origin point on your screen? Because screens can be different sizes. And the answer is, that is your origin point. That is 0, 0. That top left corner. Meaning that your X's or your columns all work logically. But your rows and your Y's, well, it goes 0, 1, 2, 3, 4, 5, and so on and so forth. So if I want to go north, I need to go negative, which is counterintuitive. Row, so to go north, I go row -1. So row is equal to current dot row minus 1. Go ahead, and white space doesn't matter here, so that's fun. Rows and current dot column. Same column, different row. Make sense? So now that I know I haven't been there before, so if this comes out true, then I haven't been there before, so I should move there. And then we can use the maze notation that we did. And we'll also want to paint our current square, or the square we're moving into, because now that's going to be a square we're visiting. Make sense? There's different ways you can do that, but you simply do this for all 4 directions. Now, what about, do I have to worry about checking out of bounds, right? If I'm on the top row, right, and I do row -1, that's going to give me rows -1. That's going to be an out of bounds exception. But here's the fun thing. Almost every programming, I think every programming language has something that's called short circuiting in them. Okay, and this handy dandy feature, which is basically following human logic, which is simply so there's a wall all around the maze everywhere. So if there's a wall to the north, because the topmost row has walls to the north, if there's a wall there, then we aren't going to bother checking this. This never runs. That's what short circuiting does. It basically says if we can determine that this entire and clause is false, then we're not going to bother checking the other side of it. Similarly with an or, as soon as we discover that something is true, we can just simply say the entire or is true. That's what short circuiting is. So that's how I can check this without having to have another clause for out of bounds. But what if you don't want short circuiting? Now, why would you want that? Because you're doing something dumb, like maybe like having a minus that you want to execute all the time, or you always want both things to run. In that case, guess what? Ever wonder why you have two of those? Because one can mean no short circuiting. If you do this, that means no short circuiting, which means we're going to get a bunch of errors. It also means logical and, also means Boolean, logical and, or bitwise and. So you can also do that with mathematics for integers, which is all kinds of weird. Yes.
Does the short circuiting still work if you were to switch the starting, like if you put visited first and then,
No, because we would be checking if we're out of bounds. We do an out of bounds check first.
so then you get the error?
Yep. That's why I have it. That's why I had it in this order I laid out in the document, so that you would instinctively do the check if there's a north wall first. Yes. Yep. That's exactly what I meant. Yes. Yes. The so what I was talking about is that you could do something. So if there was an if statement like this, the reason you might do that is if you have an if statement like this, if I is less than 5 and j plus plus, j plus plus is less than 10. So if you have a clause like that, okay, which is bad. You should never write something with an increment clause inside an if statement like that, right? If you want to increment something, you should make your own statement that does so, okay? But if this short circuits, then this clause never runs, okay? So j will never get incremented. But if you want to ensure that j gets incremented every time we run an if statement, then that's where that kind of thing comes in handy. But one of the rules that I've taken from Python that I've applied to every bit of programming is that readability counts more than anything else. After all, I mean, like the code is just going to be read more than it's written. I mean, especially by me, because I've got an entire class reading this, you know? So we do this for basically all of our other directions, else if, right? Else if, else if, else if. And then we have an else at the end, okay, of that chain for, well, we can't go in any direction, so we should pop, right? In that case, we need to backtrack, so we pop off the stack. That, which simply means that now the square that we came from is now at the top of the stack. Make sense? Now, my suggestion also is that when you move to a square, when you're moving to squares as part of a solution, you color it one color like blue. And then when you're backtracking off a square, you want to mark that it's not part of a solution, so it's easy to see. So like color that a different color like gray. Okay. If you go color dot, and it will come up with all the like pre-programmed colors. There's lots of them. And you can even make your own custom color if you want by just simply saying, hey, this is the these are the values. You just simply say new color. Okay. Does that answer everybody's questions as to how to get to the solution for this? Hopefully this like really accelerates where you are in this. I maybe should have gone into more detail with other stuff, but it's been a bit of a, it's been very busy with having to get the exams ready and just making sure that everybody's getting the Josephus done. This isn't meant to be, so again, the recursion is gonna be, again, one of the bigger assignments, and then we're gonna have a few smaller assignments until we get to Cheater's Hangman later in the semester. Okay. So, but they're all not, I do like, after the recursion is trees, which I'm gonna keep it what I have for right now because it does teach you a valuable lesson about large files, and large files are like 5 megabytes, so not that large, I guess. But interacting with them can be very weird in an IDE. All right. Anything else before I start going and demoing stuff or answering questions? Anything from chat? Oh, yeah. Yeah, I noticed that somebody did not. Okay, yes, I will make the grades public. That was, I don't know why it got set to not being public, so very easy to do that. I just simply take the syllabus up and grades over here. There, you should be able to see it again. Module assignments. Save, you should be able, once this saves, you should be able to see your grades again. Yes?
Do we have to write the solve maze view method?
No. That's still in there?
So it's in the PDF, it says something about it.
Oh, yeah, no, I removed that. I did that one semester and then thought it was silly.
But
Yes.
then what's in
It- What?
It's the towers in
This-
towers in plot.
Oh, we're gonna do that in class. It's Towers of Hanoi. I just gotta make sure I've got a date, just gotta figure out what day I'm gonna do it. Probably next Tuesday. Towers of Hanoi is a very different kind of recursive problem, rather than doing recursive backtracking. Recursive problem solving, and then you've got the last one that's also useful for interviews for recursion is recursive permutations. Really, recursive backtracking, recursive permutations are really what ones you want to hammer doing those. All right. Gonna go ahead and stop sharing and start recording.